Okay, so today we are gonna solve exact differential equations. What are those? Let me introduce them. These are exact differential equations. So what is an exact differential equation? Well, first of all, it's also a first order differential equation. And it's ordinary. That means that we have an independent variable that we're gonna call x, and a dependent variable that we're gonna call y. So y is gonna depend on x. Okay, so we want to know if such an equation that we're gonna write in this way is an exact differential equation. Well, first of all, notice something. We want the functions p and q to be functions C1 on omega, okay, where omega is a subset or R2. So what we want to look for is a solution of this equation. Notice also that this equation can be rewritten in normal form. How do we do that? Well, we can just put on one side the p, and we can just write y as a function of p, q, like this with a negative sign. Okay, so this would be the normal form. But usually if an equation is given to you in this form, most likely you have to solve it with the exact differential equation. So it's kind of a hint, but not necessarily, okay? But well, so now we say that an equation of this type is exact if we can find a solution. So we are going to look for a solution, an equation, oops, sorry, an equation of type, let's see, orange star, is an exact equation if there is a solution. Let me call it U. Okay, so U, it's a scalar function, okay, that takes values in R2, and U has to be C2 on omega. Okay, so it's an exact equation if there is a solution U that is of the following type, such that the partial derivative of U with respect to x is going to equal the coefficient p, and the partial derivative of U with respect to y is gonna equal the coefficient q. Okay, so that would be a first definition of what an exact differential equation is. Okay, but let me introduce a proposition that's gonna give us some more insight about this exact differential equations and other properties. So one thing is that given a possible exact equation that we call again P plus Q. If it's exact, as we're saying, and it has a solution U such that partial derivative of U with respect to X equals to P, and the partial derivative of U with respect to Y equals to Q, and U is C2 on omega, then Y is the solution of the exact equation and X is C1, and it is also satisfied that the U is going to be a constant. In all omega. Okay. This function U is usually called the potential function. So you know, so this function usually appears in lots of physics problems. Okay, so it's the potential in an electromagnetic field. It's the gravitational potential as well. Okay, so in these kinds of fields, one can find one of these potential functions. So given that, we can introduce a theorem. We'll go prove this proposition very straightforwardly if you want me to. So, well, let me do it. So we say that Y is a solution of P differential X plus Q differential Y equals 0 if and only if the potential function is a constant. Okay, so let me prove this. So the reverse is pretty straightforward. We start saying that C, the constant equals the potential functions. Okay, and we are supposing that Y is going to be a function of X. So that means that when I take the complete derivative of U with respect to X, considering that Y is a function of X, if we apply the chain rule, we'll have partial derivative of U with respect to X plus partial derivative of U with respect to Y and differential of Y with respect to X. And this equals, well, we can write it again, like partial derivative of U with respect to X. Here we can introduce the Y prime notation. So now we were having in mind that Px, Y, and Qxy is exact. Okay, so since it's exact, we know that the partial derivative of U with respect to X is exactly P, and the partial derivative of U with respect to Y is exactly Q. So that means that we can actually use that here. So this equals P plus Q times Y prime, but this is exactly the equation. Okay, this is the exact equation, and we want this differential to be 0. Okay, because U is a constant. So that means that this is 0, and this proves that y is a solution. Okay. The straightforward one is very easy too. So we start from y being a solution of px y differential x, but q x y differential y equals 0. Since we're supposing that it is exact, then we have the partial derivative of u with respect to x equals p, and partial derivative of u with respect equals q. So that basically means that if we take the equation, the initial equation, which was this one, and we plug the derivatives, we have partial derivative of u with respect to x plus partial derivative of u with respect to y prime equals 0. And this can actually be recast as the total derivative with respect to x of u when y is a function of x. And this is exactly 0. So this implies that u is going to be a constant. So, well, here we have proved that the equation is exact. This potential function that we are integrating is actually a constant. So that's an important thing to keep in mind. And another important thing is a main theorem about this equation. So the main theorem says that given a exact equation of the type pxy plus qxy y prime equals 0 with pq functions that are C1 on omega, we say that orange star is locally exact and omega if and only if the partial derivative of p with respect to y equals the partial derivative of q with respect to x. Okay, so this is a very important thing because this is very straightforward and it's very easy for us to prove or to double check at first if an equation is exact. Okay, so this is going to be a really great use. So one could prove this very easily. So let's do it. So we have the direct form, and the direct form is like if the equation is exact, if star is exact, then we have a solution, okay, that we're gonna call u, that is C2 on omega, and such that partial of u with respect to x equals p, and partial of u with respect to y equals q. Okay, that's just being exact, like the very first definition that we introduced. So now, as we have imposed, as we have that actually the function u is C2, that means that we can take the second derivative. So we have partial of u with respect to x, and we have partial of u with respect to y. But since it's C2, I can take the partial derivative of y with respect to y, of partial derivative of u with respect to x, and this would be the partial derivative of p with respect to y. Okay. And then on the other hand, I have that I can take the partial derivative with respect to x of partial derivative of u with respect to y, and this is exactly the partial derivative of q with respect to x. So what does this mean? Well, if it's Bart's theorem is satisfied, and remember that for this we only have to have like u be defined on an open subset that we call omega of R2, and also U2, U is C2, and the derivatives are continuous. Then we can apply this Bart's result, which is basically that you can say that the derivatives commute. And since this happens, this implies that partial of p with respect to y is partial of q with respect to x. So that's pretty straightforward. The converse, it's a bit more complicated, but it's easy too. So let me show you the converse really fast. I'll do the first part and you guys will do the second part. So here we start from knowing that the partial derivatives, the cross derivatives of these coefficients are equal. We would like to see if there exists a function u such that partial derivative of u is gonna equal p, and partial derivative of u with respect to y is gonna equal 2, and such that p plus q y prime equals 0. Okay, so how do we see if there is this function u? Well, I think the simplest way would be to propose an u and see if the u works, and if the u happens to have these partial derivatives equals to p and q, that means that we're doing it correctly. Okay, so let me propose a u, and the u I'm going to propose is the following one. I'm going to integrate p and x, and I'm going to integrate q and y. While I integrate q and y, I'm leaving the x fixed, and while I'm integrating the p and q, I'm leaving the y fixed. Okay, so I need the partial derivative of this u equals p, and partial derivative of this u with respect to y equals q. Okay, so I'm gonna check if this happens. So I start with the first one. So this would be the first one. So how do you start? Well, I'm just gonna derivate this. So see that the first one is just an integral. So the integral will be just taking the p and x, and the point y is fixed. And the second one, I'll have to take the partial derivative of the integral. And we are here using that the integral and the derivative are gonna commute. So I introduce here the derivative, and we're starting from the partial derivative of x of q with respect to x equals the partial derivative of p with respect to y. And notice we're integrating in y. So this basically means that I'm just evaluating the function p in the limits y0 and y, okay? This is y. So this means that I have px I0 plus pxy minus pxy0, and these two cancel out. So basically, I've proven the partial derivative of the u that I've chosen as the p. I can do the same thing with the second one. It's just derivating with respect to y, and you will reach the same conclusion that the partial derivative of u with respect to y is going to be q, okay? So I'm not going to do that. That's very straightforward, so you guys can prove that. So basically, what we have proven is a bunch of things for our exact equations. So let's do a summary of what we have. We have that given an exact equation that is p plus q y prime equals 0. Okay, with all the conditions that we need, that p and q are C1, okay, defined on omega and open subset of R2. We have the following things. One, that the partial derivative of p with respect to y has to be equal to the partial derivative of q with respect to x. Okay. Then we have that there exists a function u that is C2 defined on omega such that the partial derivative of u with respect to x equals p, and the partial derivative of u with respect to y equals q. We also know that this function, the potential function, is constant on the domain of definition, and also the shape of this function is the following one. Okay, so that's a little summary of what we can use to integrate this equation. So I would like now to solve a specific problem. So let's solve a differential equation. So example. I have the following one. See that it's written how I said, it's not in normal form. It's in a form that when it's written like this, the first thing that one should wonder if it's actually an exact equation. So this is what I've called P, and this is what I call Q. And I want to see if it's exact. So I know that the equation is exact if the partial derivative of p with respect to y equals the partial derivative of q with respect to x. So let's check that. So the partial derivative of p with respect to y will be the partial derivative with respect to y of x plus y times cosine. And this is only the cosine, okay? And partial derivative of q with respect to x would be the partial derivative of sine with respect to x, which is cosine. And notice that they are both the same. So we can claim equation is exact. Okay, and since the equation is exact, I know that I'm gonna have a solution, okay, of the shape that I formulated. So, and that means that this solution, its first derivative with respect to x, partial derivative is gonna equal the p, and the partial derivative of the u with respect to y is gonna equal the q. So what does this mean? Well, that I have a system of equations in which this equals p, in which this equals q. And I only have to integrate the system, which is really straightforward. So let's do it. So here's the system. I'm gonna start with the second equation because it's easier. So notice here that u of xy will be integrating the sign with respect to y when x is a constant. So we will have y sine x, and we left the x a constant. So this is the way in which we integrate functions that have several variables, okay? So that would be the first part. But then furthermore, we know that the partial of this u with respect to x has to be equal to p. So if I derivated what I got, the partial derivative of u with respect to x, it would be the y stays, the sign is cosine, and we derivate the arbitrary function of x because we were integrating with x constant before, and this has to equal p. So realize that here we obtain that the arbitrary function of x has to be x squared and a half of it. So and we can actually add a constant of integration if you wish, but it's not necessary. So this means that my u was this, and now I have my function, which is a half of x squared plus a constant. And we also know from the summary that this has to be a constant. So, well, I can rename the two constants, okay? And I can just claim that y sin x plus x squared equals another constant k, okay? And well, this is the implicit form. What can you just write if you want, like this in the normal form. And that would be the general solution of this equation